Hello, my name is Shelly Mardhia Faizy. I'm a master student from Uppsala University, Sweden. In this occasion, I would like to share my project about numerical modeling of geothermal systems and the effect of permeability, topography, and the lower system boundary. Global energy consumption is projected to increase in the future, including renewable energy, particularly geothermal energy. It is presented as a green line in this graph. Geothermal energy has been used as a thermal spring, building heating, and notably to generate electricity. In order to keep exploration costs low, numerical modeling used as a fundamental tool to predict potential field of new geothermal system. However, most current numerical models concentrates only on the shallow part around the heat source, ignoring the deeper part of the system, as it can be seen in this model by Heiba and Inget-Britsen, also by Arnessen. Both literally cut off the layer below the intrusion. This led us to come up with research question: what is the effect of lower boundary in geothermal system while changing the permeability and topography of host rock systematically? Our study case based on cerobiolaccolith, a fossil geothermal system in Chachahuan volcano complex in Argentina. We use hydrotherm from USGS for the numerical modeling. Input parameters was obtained from thermobarometry analysis and literature review. Geometry of the models are set with four types of topography scenario. First is no topography scenario, for example, flat topography. Then topography based on volcanic type, which is stratovolcano, caldera, and shield volcano. Each scenario has two versions of model. First, model with intrusion and an added layer below the intrusion. The second, an intrusion and an impermeable layer just below the intrusion. Additionally, for the direct comparison to investigate the effect of lower boundary, a model with a bottom layer removed below the intrusion was built only for flat topography scenario. Here in this result and discussion part, first I compare an added layer versus standard model in flat topography with high permeability value. For both models, it formed a small plume within 50 years. The difference starts showing through the times. In Model A, as a result of stronger convection in the system, it generates multiple plumes within 2000 years. It is also formed a cold spot below the intrusion. While in Model B, as a result of weaker convection in the system, it only generates a broad plume. Another observation, Model A has stronger convection since it has bigger geothermal system compared to Model B. Therefore, it tends to get cooler earlier than Model B. The comparison between the two models show that the bottom boundary fundamentally affects entire system evolution. To have observation in the effect of permeability, we ran a simulation with the same condition and scenarios with the model A1 and B1 from the previous slide, but having lower permeability value. The models does not show any formation of plume. It is indicated that it controls by conduction. Hence, lower permeability will cause a conduction regime. It shows total contrast behavior from high permeability models. Moreover, temperature intrusion in model A2 decreased early than model B2 since it has bigger geothermal system. For further investigation to confirm on the effect of lower boundary, we add an impermeable layer just below the intrusion. Overall, this model shows similar evolution to those where the bottom boundary is placed there. This suggests that the modeling standard of cutting the model below the intrusion is valid for certain geological cases. To see the effect of topography, we add three different topography scenarios. Generally, the three models show similar thermal structure such as small plume at the right corner intrusion, multiple plume as a sign of convection, as well as the formation of cold spot. Hence, the thermal longevity is specifically different between these three models. In these models, the caldera models, which has the more shallow depth of emplacement for intrusion, it revolves slowly. It keeps the heat longer compared to strato and silt volcano. Here, it shows that topography also has influence in overall system evolution. Investigation with impermeable layer is run in the volcanic topographic model as well. The overall behavior is still equivalent with models where the bottom boundary get cut. This is also confirmed the effect of lower boundary in the system. As it mentioned before, there is a low thermal anomaly which always show up on a models with added layer, even when the impermeable layer placed just below the intrusion. This figure here presents a closer look on the anomaly. This anomaly occurs when the cold water at the top encounters the bottom of the intrusion. At the bottom of the intrusion, we can see there is accumulated heat source which developed through thermal conduction. By transferring the heat, the fluid has cooled. This makes the fluid more denser, causing it to move downward, as it can be seen from the down movement of the vectors. This thermal anomaly could be associated with the hydrothermal alteration in the system. To conclude, an added layer indeed has strong influences in the dynamic of geothermal system because it changes the specific of system evolution. Nevertheless, overall behavior related to effect of permeability and topography is still similar with standard models. And then a caldera volcano traps heat below the caldera, whereas silt and stratovolcano topography push heat away from below the edifice. A low temperature anomaly develops on permeable systems below the intrusion in all models with an added layer. Lastly, the findings of this study can be implemented as future investigations, particularly in assessing the geological applicability of numerical models in geothermal systems. It also can be used for pilot study on exploration geothermal system or formation process and geophysical explorations. Thank you.